let's focus on the proton for the time being, because the vast majority of hydrogen atoms we have in molecules, organic molecules certainly included, vast majority of hydrogen atoms we find naturally. They are almost all of them are protons, because if you check the natural abundance of hydrogen, over 99.8% they are proton, H1. There you have 0.1 something percent, they are H2. And the H3 is radioactive, not stable. Okay? So for practical, the purpose, we can say pretty much all the hydrogen atoms, they are protons. Okay, but let's say look at those hydrogen atoms. In most of molecules, especially organic molecules, almost all hydrogen atoms, they are bonded. Okay, bonded means the hydrogen atoms, they are not only the proton, they also have what? If a hydrogen atom is bonded, other than the proton, what they have? The electron, right? They always have electrons around it. So the electrons have around the proton makes all the difference in the proton NMR. Just keep in mind, the electrons around the proton makes all the difference. All the difference you will be seeing in the proton NMR. Why? Because electrons around a nucleus, like a proton, they respond to magnetic field. They will undergo circulation. If the electron originally like randomly move around, if this nucleus originally the electrons randomly move around the nucleus, okay, and the probability is described by wave function, okay, originally, okay. But if you put in magnetic field, you will start undergo circulation, okay, and that circulation depends on the magnetic property of the molecule. Vast majority of organic molecules are diamagnetic. That means the circulation of electrons will be in such a direction will generate a magnetic field oppose external magnetic field B0. Okay, so like the one we're seeing here, if the B0, let's say, is going up from the bottom, going up, okay, and then I have a proton here with some electron around it, then circulation of electrons will create a field, small field against it. So big magnet is going up, the circulation of electrons can generate a field, small field against it. Okay, so this small field strength we call it BE. Okay, is actually very, very important. Okay, although this BE usually is very, very weak, only is a few ppm of the original field strength. You know what a ppm is? Can you tell me ppm? What does that mean, ppm? Yeah. Parts per million. Very good. Parts per million is one out of a million. So this BE usually is the about a few ppm of the original one, okay, B0. So this change is small, but the modern NMR instrument is sensitive enough, can detect 0.00 something ppm. Okay. So that's what makes all the difference. Okay. So because of this BE is opposed of external field, so the field really experienced by, let's say, this nucleus is no longer B0, is a B0 minus BE. BE is a circulation of BE is a magnetic field, okay, generated by circulation of electrons under the influence of the external magnetic field. Okay, so this is one. BE. Let's say if this electrons circulation of electrons, okay, you put in the magnetic field, the electrons start to circulate. And the circulation electrons generate a field BE against external field. So the net effect, because you have electrons around the proton, those electrons will circulate under influence of magnetic field, and the circulation of electron will generate a field that's against the external field. So the net magnetic field experienced by nucleus is a bit weaker because the fact the nucleus has the electrons around it. Does it make sense to you? Because you have electrons around it, and you put that electrons around the magnetic field, the electron will circulate. And the electron circulation will generate field against the external field. So this the generator, this is the magnetic field generated by circulation of electrons. Because this field is always against the external field. So the real field, effective field, experienced by the nucleus is B0 minus BE. Now the key part is here. Now every proton, the electron density around every proton generally are different. So if a proton has a higher electron density, that means the electrons around that proton, well, the circulation of the electron around that proton will generate a stronger BE. This field will be stronger, okay? This field will be stronger. And then the BE effective BEFF will be weaker, okay? So this is the major principle of the proton number, if you want to understand the resonance frequency. Okay? So the high electron density around a proton, the greater the BE will be. And if the B is greater, the B0 is fixed, right? Then the effective magnetic field will be weaker. So we say that if we have a proton have electron around it, we say the proton is shielded by the electron from the magnetic field. Okay, because of due to the presence of electrons, make the effective magnetic field experienced by the nucleus weaker than the external field strength. So we say the electrons shielded the proton from the external field. And the high electron density you have around the proton, the greater the BE it is, and the smaller the BEFF will be. We say the more the proton is being shielded by electrons. And what's the impact of change of the BEFF? Because keep in mind, resonance frequency is directly proportional to magnetic field. And to be exactly correct, this magnetic field is not the external magnetic field. This magnetic field is the magnetic field experienced field by the proton. So that means the electron density around a proton can directly impact its resonance frequency. See, if the electron density around a proton is higher, okay? So if electron density is higher, this one will become what? If electron density around a proton is higher, that means the circulation of electrons, okay, under the influence of magnetic field will produce a weaker or stronger BE if the electron density is higher. Say if let's say you have proton or have electron around it, okay? If electron density is higher, the circulation of electron will produce a stronger or weaker BE. High electron density, stronger BE, and then the effective magnetic field will be weaker, okay? Because of the effective magnetic field is B0 minus BE. Okay? So then that means the most important relationship is the high electron density you have around the proton, then it's the resonance frequency will become lower, because the higher the electron density is, this one will be greater because you have more electrons circulating under influence of magnetic field. So this one will be greater, okay? This one is fixed, so this one will be weaker. If this one is weaker, the resonance frequency becomes lower, okay? So this is the most important concept in proton number. Here is just the pretty much using the figure to present this. If it's isolated proton, no electrons around it, the proton fields, full strength of the magnetic field, okay? But if you have electrons around it, the circulation of electrons gonna generate, okay, a magnetic field, small magnetic field, we call it BE, okay? And this BE is proportional to external field, because after all, this BE is a result of interaction of electrons with the magnetic field. So this BE is always proportional to the external magnetic field, B0. And this sigma is called screening constant, okay? This is a constant independent of the magnetic field strength of the instrument. It's only dependent on the chemical environment of proton. And this sigma, okay, usually is dependent on the electron density around the proton. So that means if you look at it, the effective field of a proton field is B0 minus BE equal to B0 minus sigma B0 equal to B0 times 1 minus sigma. And then the resonance frequency, we know, is proportional to the magnetic field. K means just a proportional constant, equal to a K times B0 minus 1 minus sigma. Okay. So resonance frequency of a proton is directly related to its screening constant. Okay. Now we know that resonance frequency, okay, of a proton is directly proportional related to the screening constant or electron density in most of cases. But the directly using the raw resonance frequency is problematic for two reasons. First of all, we know the resonance frequency depends linearly on the magnetic field strength. Okay, so if you want, report raw frequency, the magnetic field strength must be reported. Okay, and also a raw frequency includes no standard of comparison. So if you only have a resonance frequency, you don't really know how can you directly derive the structural information. Okay? So to address both these two issues, chemists invented a parameter or a term called chemical shift, addresses both of those two issues. Okay. So the chemical shift, okay, is using a Greek letter delta to represent it. It's defined as the position of signal. Position means resonance frequency of a particular proton, or later carbon-13, same thing, just resonance frequency of a particular nucleus minus the resonance frequency of one reference compound. Okay, means this reference compound is TMS, tetramethylsilane. Okay, so one of the reasons, for chemists, okay, to pick TMS as a reference compound is because of let's say, if we're looking at the proton and the NMR, so we all know that we are looking at the protons, the hydrogen. Okay, so we just made the argument. I hope you accept that. The resonance frequency is give you the information of electron density. So it's convenient for us to have a reference compound, either have a proton with extremely high electron density, or a reference compound, with the proton with extremely low electron density. So for whatever reason, chemists pick, a reference compound with the electron density of the protons extremely high. Okay, so why? So basically what you see here is you have those totally 12 protons in a single compound, 12 of them. Okay, and each of those protons, okay, they are actually has they have very high. Each of them has a very high electron density. Okay, why they have very high electron density? Because as you know, silicon, okay, is a element sit below carbon. So silicon electron activity is higher or lower than carbon, sit below carbon. So it's lower than the carbon. Okay? So silicon actually will donate, if you look at inductive effect, silicon will donate electrons to those methyl carbons. Okay? When the methyl carbon is very electron rich, then the carbon also going to push some electron back to those protons. So that makes the protons in the TMS is unusually electron rich. So the electron density is very high. Okay. So pretty much all the protons in organic compound will have a lower electron density than the protons in TMS. So that's just one of the reasons, you know, we use TMS as a reference compound. So if a proton has a low electron density than the proton in TMS, then the resonance frequency will be higher or lower. So if the TMS, okay, if the proton in TMS, they have a high electron density than any other organic compound, okay, say 99.99 organic compounds. So the protons in those organic compounds, because they have a low electron density, that means the resonance frequency will be higher or lower than TMS. Higher, okay? Low electron density is a higher resonance frequency, okay? So that makes it convenient to make this guy chemical shift, make it as 0, right? So pretty much all the protons you see will have positive chemical shift. This is just convenient. The other reason of TMS is also because it's a pretty stable compound. Okay, so pretty much all the protons in organic compounds, they have a low electron density than the protons in TMS. Therefore, they have a higher resonance frequency, so they can have a positive chemical shift value because you take the resonance frequency of your signal of interest minus the resonance frequency of TMS. Then divided by the spectrometer frequency times the milli. Okay, so if you look at this one, chemical shift technically does not have unit because you see here the position of signal is the frequency hertz. Okay, this one also hertz. The spectrometer frequency also is hertz. Hertz divided by hertz, no unit. Okay, so the chemical shift itself doesn't have a unit. If you really want to call it unit, we can say ppm. That's fine, because the chemical shift we have is something times a million. So really wonderful unit called ppm is fine. Okay. Now, if you look at a little more details, if you look at a chemical shift and putting the how resonance frequency is impacted by screening constants, you will see that by definition, chemical shift is the resonance frequency of your sample minus the resonance frequency of TMS divided by the instrument frequency. Okay, so the instrument frequency is just constant times B0. That's the magnetic field strength of the instrument. Okay, and for the sample, the resonance frequency, as we know, is KB0 times 1 minus sigma s. Sigma s is screening constant of the proton of interest, and this will directly reflect the local environment of the proton of interest. We're going to discuss those things in great detail. Okay, and obviously the resonance of TMS is 1 minus sigma TMS. So what you can see, the chemical shift value is only related to the screening constant difference of the proton of interest under the screening constant of the TMS. So chemical shift, okay, is only related to the chemical nature of the proton of interest. Has nothing to do with the instrument. This is the best part of the chemical shift concept. So you can chemical shift only reflects the chemical nature of the the particular nucleus of interest. Has nothing to do with instrument. Has nothing to do with magnetic field strength. So chemical shift directly only relate to structure. There's nothing else. Okay? Only relate to molecular structure. Nothing else. Not the instrument, not who operated. Okay? Only relate to the structure of the proton of interest. Okay? So here just the one of the example of NMR, the spectrum. So the NMR spectrum usually is presented as a plot. The y-axis usually we don't really show the unit, but the y-axis is the absorbance. Y-axis is absorbance. It means how much electromagnetic wave is being absorbed. Okay, absorbance. Okay. The x-axis is a chemical shift, so called delta, and it doesn't really have a unit, but because the chemical shift definition is a screening constant times a million, so we usually just call ppm. Okay, so the chemical shift, just for historical reason, we on the x-axis we write the smaller chemical shift level to the right and the larger one on the left. That's just historical reason. So this particular NMR spectrum has a single proton. We're talking about proton NMR. Okay? We're not talking about carbon-13 yet. Okay? Just talking about proton. Why are we talking proton first? Because of two reasons. First, if you have a same number of protons and the carbon-13, the proton alone give you much more intense signal than the carbon-13. Just equal number of proton nuclei and the carbon-13 nuclei put in the same instrument, the proton sample will give you stronger signal than carbon-13. So that makes the detection or collection of proton NMR much easier than the carbon-13 NMR. This is one. Okay. Second is because of, as we know, the nature abundance of the proton out of all the hydrogen we're going to deal with almost 100%, 99.8, 99.9. I don't remember exactly, but it's more than 99.8. Let's put this way. But the nature abundance of carbon-13 is only 1%. Okay, so that makes the collection of proton NMR spectrum even easier than the carbon-13 NMR. So that's the reason why proton NMR is the most popular kind of NMR technique. Basically, it's much easier, much more sensitive than carbon-13. So let's say for proton NMR, in order for you to get a reasonable quality spectrum, you only need about 1 milligram sample. Usually 1 milligram. Okay, but for carbon-14 NMR, if you want to collect the equal quality sample, even with longer time, you need about 50 milligram sample. Okay, yes. Oh, we'll talk about later. That's what we'll talk about later. We'll talk about that. Okay, if you have multiple protons, right? Then we'll talk about it. We'll talk about it. We're gonna learn how to read. Yeah, we'll talk about that. Okay, that's the topic. But the whole reason why we focus proton first, because proton NMR is a lot easier to collect, much higher sensitivity. Okay, and in many cases, proton NMR, as you will see, also potentially provides more structural information, okay, than carbon-13 NMR. Okay. So here's one example. This is a compound, chloroform, trichloromethane. This compound is the simplest compound because it only has single proton. So I want to, it's very like you ask question about if you have multiple protons, how do we know whether are same or not? That's your question, right? We will see. Okay, but this one is easy. Only got one proton. Okay, so the only one signal. So it's absorbed at 7.28 ppm. Okay, so that's just the simplest NMR spectrum. We will be seeing, but first, okay, as we know, this chemical shift value, okay, is a reflection of resonance frequency, and the chemical shift value is a reflection of the screening constant, and the screening constant is a reflection of electron density. So obviously, the chemical shift value of a given proton gives you the information about electron density. Okay? So this is the first thing we're going to look at. The chemical shift value carries structural information. Okay? Carries, yes? What? Oh, this one? Yeah. These are not signals. These are satellite peaks. They don't worry. Okay? This is just one peak. Singular, we're going to talk about that. Singular means one signal, only one peak. A signal with one line is not singular. Yes, that's correct. Singular. Yeah, we will talk about later on. But that is right. It is singular, but we will talk about later on. But first let's talk about the chemical shift value, because chemical shift value carries very important structural information. It's implied, okay? But at least you know the trend. Okay? So first, we want to see how molecular structure impact the chemical shift value. So the first thing is, again, let's focus on electron density. Okay? The most important concept, if you talk about consider the chemical shift value of proton, think about electron density. If electron density for those protons of comparable structure, if electron density is higher, chemical shift value will be quicker. If electron density is higher, chemical shift value will be yes, please louder. If electron density is higher, chemical shift will be lower. Okay, those are general trend. Okay, because if electron density is higher, its circulation will create a stronger field. Okay, this stronger field will cancel the external field more, and that makes the real field experienced by the nucleus weaker. Weaker means resonance frequency is lower. Okay? So high electron density will give you lower resonance frequency. Lower resonance frequency means lower chemical shift. Okay? But anyway, look at here. Those are the 5 compounds. Okay. So the TMS, we know that that's a reference compound. Chemical shift value is reference. We set it as 0. Okay. This was just artificially set as 0. Okay. And then if you look at the FM, the resonance frequency, the chemical shift value is 0.9. Why? Is this guy chemical shift value is a bit higher than the TMS, because silicon, okay, is less electronegative than carbon. Okay, so silicon gonna donate electron density to the methyl group, so makes the proton in the methyl group has a high electron density than the protons in ethane, because silicon donate electron to the methyl group. Okay, donate from basically here. Under the ethane, well, the electron density, is pretty much mostly related to carbon-hydrogen interaction. So you will see it's a little bit, the higher than the TMS. And then now try methylamine. You compare these two guys. As we know, nitrogen is somewhat more electronegative than carbon. Nitrogen is 3, carbon is 2.5, 2.6. So somewhat more electron than carbon. So nitrogen gonna steal some electron density away from methyl to nitrogen. So the methyl proton here, electron density is lower than the methyl proton here, because each methyl proton gonna lose some electron density to the nitrogen. a little bit, not too much. Okay. Now here, compare this one to this one, the oxygen is more electronegative than nitrogen. Again, somewhat 3.5 and 3. Okay. So the oxygen can steal more electron away from the methyl carbon. And the methyl carbon has no choice, has to get something compensation from the proton around it. So that makes the proton electron density here is lower than this. Okay. Now the fluorine, we know it's not the most electronegative element. So it will steal electron density away from methyl carbon by inductive effect to the largest degree from the single atom. Okay. Then this guy is overly electron hungry. Oh, so I'll get some compensation from hydrogen. Okay, so that's why the methyl proton here has the lowest electron density. Okay, that's why the chemical shift value is highest. Any question about that? All about electron density argument. Okay. Now even for this guy, okay, propane, there are actually two kinds of protons. One is a methyl proton, one is a methylene proton, CH2s. Okay, what you can see is the methyl proton chemical shift value is a bit lower than the methylene proton. Why? After all, carbon has somewhat a high electronegativity than hydrogen. Carbon is 2.5, 2.6. Hydrogen is about 2.1. So carbon is somewhat higher electron than hydrogen. So every carbon gonna steal some electron density away from hydrogen if we consider inductive effect. If you look at methyl proton, you have 3 hydrogen atoms to satisfy the electron stealing power from one carbon. These 3 hydrogens, you have 3 of them, right? It can satisfy electronic needs of a single carbon atom. But here, you only have 2 hydrogen atoms connect to this carbon. So these 2 hydrogen atoms, they have to share the burden to satisfy the needs of this single carbon. So that's why if you look at the, basically these 2 hydrogen atoms, each one of them gonna donate a bit more electron density to this carbon than those 3 hydrogen atoms, okay? Which 3 of them can feed 1 carbon. Here, 2 hydrogen feed 1 carbon, okay? So after feeding this carbon, the methyl proton gonna have a little bit of high electron density left compared to the methylene proton.